Hello everyone, I'm Daryl Heath with UA Little Rock's College of Arts, Letters, and Sciences. Welcome to the night sky. How can astronomers possibly know how far away stars and galaxies are? I mean, there's no tape measure in existence that can give us that kind of information. So how do they do it? The first method that astronomers ever used to measure the distances to the stars was something called parallax. Now let me give you a quick demonstration of what I'm talking about. I'm going to ask you to play along, but be warned, you might feel a little silly if you're doing this out in public. I want you to hold your thumb up and extend your arm all the way out. Now, looking at your thumb, I want you to blink one eye and then the other. Notice how your thumb seems to shift back and forth with respect to objects in the distant background. This is easily explained as you are looking at your thumb from a slightly different angle with each of your eyes. Hold on though, your embarrassment isn't over just yet because I want you to now hold your thumb right in front of your nose and repeat the exercise. This time, you'll have noticed that your thumb had a much larger shift with respect to those background objects. We can actually calculate the distance to nearby stars by measuring how much they shift relative to more distant background stars. First off, we must establish a baseline. When we did the exercise of holding our thumbs out in front of us, the distance between our eyes was our baseline. But when measuring something as far away as a star, we must have a really big baseline. Astronomers will take a reading on a given star's position upon the sky, and then 6 months later, when the Earth is now on the opposite side of the Sun, they take that same reading again. By knowing the size of the Earth's orbit, they can establish this requisite large baseline. After getting their two separate readings of the star, they can measure how much of a shift occurred in its position with respect to the background stars. With the baseline established and by measuring the amount of parallax shift, astronomers need only apply some trigonometry to calculate the distance to a star. But there's a problem. The stars are really far away, and the amount of parallax shift is very tiny and very difficult to measure. In fact, telescope technology did not allow us to even make these kinds of measurements until the year 1838. The stellar parallax method only allows us to measure the distance to nearby stars, say within 100 light years of Earth, 1 light year being the equivalent to about 6 trillion miles. Clearly, in order to measure further distances, we would need a different kind of tape measure. Henrietta Swan Leavitt to the rescue. Henrietta Leavitt, daughter of a congregational minister, was born in 1868 in Cambridge, Massachusetts. During her senior year at Radcliffe College in 1892, Henrietta took a course in astronomy and fell head over heels in love with the subject. After her graduation, Henrietta became seriously ill and was left deaf for life. She would suffer various debilitating illnesses off and on for the remainder of her life. By 1894, Henrietta was eager to find work in the field of astronomy. Unfortunately, in her day, women were not encouraged to seek careers in any field, let alone one in the sciences. However, at the Harvard College Observatory, the director, astronomer Edward Pickering, had a problem. It seems that his observatory was collecting far more data than his astronomers could handle, and he would have to hire a staff to do a lot of grueling, monotonous computational work. If he hired men, he would be obligated to pay them a decent salary, and his budget was limited. However, women were considered cheap labor, and his budget would just cover a staff of female computers, as they came to be known, or less flattering, and within certain circles, they were sometimes referred to as Pickering's harem. Henrietta joined this group of women in order to be a part of astronomical research, even if it meant not using her intellect to its fullest potential. Because she was a woman of means, even though limited, Pickering did not pay Henrietta a salary at all. She initially worked entirely as a volunteer. The other women usually earned about 50 cents an hour, slightly more than what a factory worker would have earned in those days. Eventually, Pickering did award Henrietta a salary of 30 cents an hour, and he placed her in charge of poring over glass photographic plates, looking for variable stars, stars whose brightness changes over time. It's doubtful that Pickering expected Henrietta to find anything noteworthy amongst all this data, But, as it turned out, she would make a discovery that would revolutionize astronomy and our understanding of the universe. Henrietta's particular expertise was in finding a type of star known as a Cepheid variable. They get their name because the prototype star is Delta Cephei, a star in the constellation of Cepheus, and which is well placed for viewing in the evening during autumn. Cepheids vary their brightness in very regular and consistent ways. We now know that these stars are in an unstable part of their lives, and that the changes in brightness are due to changes that are going on inside the star itself, changes that causes the star to physically expand and contract. As the star expands, it becomes dimmer, and when it contracts, it becomes brighter. Depending on the individual star, this process can take place over one or more days, but it does so with clockwork regularity. Henrietta's genius was in noting a definite relationship between a Cepheid's brightness and the length of time it took to complete a cycle. In other words, Cepheids that took the longest time to complete a cycle turned out to be the brightest, while those that took shorter amounts of time were much dimmer. What's more, she asserted that their periods were associated with their intrinsic physical brightness. This is important because if you have two Cepheids that share the exact same period of variation, then the one that appears brightest to our eyes from here on Earth must be the closer of the two. Now, if you can calibrate the intrinsic brightness, the real brightness of a Cepheid variable, and then compare it to how bright the star appears to our eye, its apparent brightness, it then becomes possible to calculate its distance. Let's say that you're on a hilltop, and off in the distance there's a light bulb that you definitely know is shining at 100 watts. By knowing its actual wattage versus how dim it appears to your eye, you can calculate the bulb's distance from you. The same applies with the Cepheid variable stars. Henrietta Leavitt published a paper in 1908 titled 1,777 Variables in the Small Magellanic Cloud, and it became one of the most important papers in all of astronomy. After the necessary calibrations were completed on Cepheid variable stars, in 1920, astronomer Harlow Shapley, using Cepheids found in globular star clusters, was able to determine that the solar system is not at the center of the Milky Way galaxy, which, by his estimate, was located some 50,000 light-years away from us. We now know that it's closer to 25,000 light-years away. He would go on to use Henrietta's discovery to work out the dimensions of our home galaxy. He calculated that it had a diameter of some 300,000 light-years. With more refined data, we can now say that it's about 100,000 light-years wide. Shapley believed that the Milky Way galaxy was the entire universe. Up until his time, astronomers had noted the existence of peculiar spiral nebulae through their telescopes. Some astronomers argued that these spiral-shaped structures existed solely within the galaxy. Others, however, hinted that they might be vast gatherings of stars that existed outside the galaxy. In 1924, American astronomer Edwin Hubble announced that he had found a Cepheid variable star inside the Andromeda Nebula, and that far from being a gas cloud inside our own galaxy, it was a galaxy in its own right, that, along with many others, existed outside our Milky Way. Overnight, Edwin Hubble, using the work of Henrietta Leavitt, more than doubled the size of the known universe. Sadly, Henrietta did not live to see just how important her work would become in our understanding of the universe. On December 21, 1921, Henrietta would die at the age of 53 in Cambridge, Massachusetts, after a long bout with stomach cancer. Henrietta's Cepheid variables are known in astronomy as standard candles. Since her day, there have been other standard candles discovered. Some are other types of variable stars, and even a certain type of supernova. All of them have known absolute magnitudes of brightness, and by measuring their apparent brightness, astronomers can then calculate their distances. Collectively, these standard candles form what's known as the cosmic distance ladder, and they have allowed us to measure distances out to billions of light years. But we wouldn't have been able to have gone so far if it were not for Henrietta Swan Leavitt. If you would like to learn more about Henrietta Leavitt and the women of the Harvard Observatory, be sure and read Dava Sobel's excellent book, Glass Universe. One of the ways that amateur astronomers can still make valuable contributions to the science of astronomy is by recording data on variable stars. It's also just a fun activity to engage in. If you would like to be a variable star observer, become active in your local astronomy club and become a member of the American Association of Variable Star Observers. Also, please visit the Night Sky webpage each month to learn more about what all is happening in your sky. Until next time, make sure you step outside every now and again to look up in both awe and wonder.